Hello, good morning, good evening, good afternoon, everybody, wherever it might be. It is my great pleasure to welcome KANG from Korea. So for you, it's the middle of the night, right? What time is it in Seoul right now?
It's 12 a.m.
Okay, so I was right. So we really appreciate your sacrifice and that you still will give a talk even though it's night for you. But on the other hand, we have people in Brazil where it's still quite early. So welcome everybody, and without any further ado, now we will enjoy a categorical interpretation of continuous orbit equivalence for partial dynamical systems. So full explanation for partial dynamical systems. It's all yours. Take it away.
Okay. And thank you for giving me a chance to speak here. I'm going to talk about categorical interpretation of continuous orbit equivalence for partial dynamical system. So the continuous orbit equivalence play a key role in connecting topological dynamical system with the syzygy radius array. So first, let me introduce one remarkable result about it. So a topological dynamical system consists of a compact Hausdorff space X together with a homeomorphism from the space to itself. We call such a system is minimal if every point has a dense orbit. That is, the forward iterate of any point eventually come arbitrarily close to every point in the space. Then a minimal dynamical system is called contour system if the underlying space is a contour set, meaning it has a countable basis of Klopen set and no isolated point. So then we say that two dynamical systems are orbit equivalent if there is a homeomorphism F from x1 to x2 that matches orbit between the two systems, meaning that for every point x in x1, the entire orbit of x under P1 is sent to by F the orbit of Fx under P2. We call such map F an orbit map. And furthermore, for each point x in x1, there is integer nx and mx that describe how the action of P1 and P2 align through F. The first condition means that applying P1 to X and then mapping it with F is the same as applying P2 to Fx a certain number of times, Nx. The second condition says that applying P1 multiple times to X and then mapping it with F is the same as applying P2 once to Fx. This condition shows that the system may not move at the same speed, but their orbits are still structurally matched by F.
Sorry, just a quick question.
Yeah.
Those functions phi1 and phi2 are invertible. Those are homeomorphisms, yes?
Yes, it's a dynamical system, so P1 and P2 has to be homeomorphism.
Okay.
Yeah. Here, homeomorphism P.
Homeomorphisms. Okay, thank you.
Yeah. So here, if the system x1 P1 is minimal, then the map M and X from x1 to the integer group are uniquely defined, and we call such map M and N the orbit cocycle associated to the orbit map F. And now here is a formal definition by Giordano, Putnam, and Scow. And two minimal dynamical systems are said to be strongly orbit equivalent if there is there exists a map F from x1 to x2 that matches the orbit of two systems. In addition, the function m and n must have at most one point where they are not continuous.
Oh, sorry.
Yeah.
I have a good.
Okay, but what does most one point of this continuity, that this range of those maps are two valued, or? Ah, no, okay, this x1 could be non-connected, yes? Disconnected, and then, okay, I withdraw my question.
I have a question.
Yeah.
The name orbit co-cycles.
Yeah.
Does it mean that it is they are co-cycles with respect to some co-boundary map? What was the meaning of the co-cycle in this phrase, orbit co-cycle?
I'm sorry because I just
These are functions. Do these functions satisfy some co-cycle condition, co-cycle equation?
I think so. But I don't know now what exactly it is.
Okay.
Thank you.
Okay.
So sorry.
Okay, go ahead,
please.
Yeah. So
You get the cycle to the group point, the
group point center. Yeah. Probably, yes.
So here is a theorem. It says that when you have two dynamical systems defined on contour set, if the systems are strongly orbit equivalent, then the associated cross products are isomorphic and vice versa. So this theorem shows a deep connection between the dynamical system and the sister algebra. And then this result has been generalized in various directions. And one such direction is the work of Carson, Lewis, Sims, and Tomford, which characterize continuous orbit equivalence for global action via groupoid and cross-product isomorphism under the assumption of torsion-free and abelian essential stabilizer. I won't go into the detail here, as I will be extending this result to the setting of partial dynamical system, and will present the details in the context of partial dynamical system. So from now, I will start my talk here.
Sorry, may I have another question?
Yeah.
Could you explain this essential stabilizer thing?
Well, I will explain it later in the context of partial dynamical system.
Okay.
Because it's So actually, my talk will start from this point. So first, let me explain what is a groupoid. A groupoid is a group-like algebraic object where the composition is only partially defined. The groupoid is group-like, but the product may not be defined for pairs in G. So here is a formal definition. A groupoid is a set with two operations, the multiplication and inversion. Also, it has a subset called composable pair, G2, which tells us which element can be combined. And the main rules are, first, you can combine element in any order as a shape. And so second is every element has an inverse. And the third one says that combining an element with its inverse gives a consistent result. So here we call the set G2 the set of composable pairs. So here is a short picture of a groupoid. So each element in a groupoid can be thought of as an arrow, like here. And the range map gives the end point of this arrow, and the source map gives the starting point of the arrow.
You mean source map or sour map?
Source map.
Yeah, but you wrote sour.
Sorry. So there should be R here. Yeah,
C,
there was.
yeah.
Yeah, C.
Yeah.
Yeah, sorry.
Yeah, and I believe you misspelled Putnam. You put E instead of A in the surname E.M. Putnam on your previous slide.
Yeah.
Sorry for the interruption.
No. I'm sorry for the misspoken. Anyway, and then the we can also think about the unit space, which is the set of all the image of the range map, which is also equal to the all image of the source map. We denote it by G0, and then the composable pair. A pair of elements is composable if the source of the first element matches the range of the second. So for this element, we can only multiply for this kind of element. And then topological groupoid is a groupoid with a topology where multiplication and inversion are continuous. And then given a local compact Hausdorff groupoid G, the groupoid G is ethyl if its range and source map are local homomorphism, meaning they act like homomorphism locally. And then the isotropy subgroup of a groupoid consists of all the elements where the source and the range are the same. And then for each unit U in the unit space, the isotropy group Nu is the collection of all elements in the groupoid that starts and ends Nu. And a groupoid is called torsion-free if for every unit, the isotropy group at that unit has no element of finite order except U. Then here is
just a quick question. This isotropy subgroupoid is in fact always a group, yes?
No. Isotropic group Nu is always group with unit U.
It's a subgroupoid because you still cannot compose things at different points.
Okay, you could have two different units. Okay, with this condition, yeah, of course.
Like a family of groups.
Exactly.
Sure.
It's like a family of groups. Yes.
Okay, yeah, of course.
Yes, here is one example of ethyl groupoid. So a diagonal system is a pair X sigma, where X is a local compact Hausdorff space, and sigma is a local homomorphism from one open set, domain of sigma, to another open set, range of sigma. And then we define the domain of sigma by looking at the domain of the previous power of sigma, inductively like this. And then each sigma n is a local homomorphism. And when you combine sigma m and sigma n, it's the same as applying sigma n plus n on the right domain. And then the diagonal lunar groupoid is a system X sigma, consists of triple of the form X m minus my, where X and Y are points in the domain of sigma n and domain of sigma m respectively. And this triple belongs to the groupoid when applying sigma n to X and sigma n to Y gives the same point. Then this groupoid has a topology, which is just a way to define how we think of point being close to each other. So let me skip in detail. And then this diagonal groupoid is locally compact, Hausdorff, and amenable groupoid. And then the unit space of the groupoid consists of triple of the form X0X, which you can think of as just the original space X itself. And then let me introduce the definition of partial dynamical system. A partial action of a group G on a topological space X means that the group doesn't act on all of X, but only on certain open subset. So for each group element in G, there is an open subset UG of X, where the action of G is defined. And then this set must follow two rules. First one is the identity element of G acts everywhere on X and does nothing. Also, applying G2 and then G1 should be the same as the applying G1, G2, but only where both action makes sense. And then this triple X3 bar P is called a partial dynamical system. So when we have a partial dynamical system, we can consider a transformation groupoid, which is defined as the set of pair Gx, where G is an element of the group G, and X is a point in the domain where G can act. In this group, the source map sends Gx to X, and the range map sends Gx to the image of X under the action of G. And then the composition of two elements goes like this. Here the source of this element is the same with the range of this map, and we can multiply these two, and this goes to like here. And then so we can also consider the inverse of Gx, which is the G inverse comma G dot X. And so we denote this transformation groupoid with this notation.
Now I have a question.
Yeah.
In geometry, there is such a notion of a pseudo group. Is a pseudo group a special case of this construction, or they are disjoint notions?
Pseudo group.
Pseudo group.
They are related, but they're not exactly the same thing.
It is the same thing, actually.
The same thing.
Okay.
Okay.
It is the same thing, right?
In particular, it's a special case.
Or there are a couple of different competing definitions of pseudogroup, and for some of them, it's not the same thing.
It's not exactly the same thing.
Yeah, I just pulled it out on Wikipedia, and it looks at least very similar at first glance. Okay.
Therefore, I asked the question.
Okay. Thank you.
Okay, thank you. And so now I will introduce the notion of Orbital morphism. So now suppose we have two partial dynamical systems. One where a group G acts on a space X, and another where group H on a space Y. And then an orbimorphism between these two systems is made up of two continuous maps. One map called P from X to Y, and then the other map called A keeps track of how element of G corresponding to the element of H, depending on where they act in X. So, and then this pair of maps must satisfy two conditions. The first, the map P should respect the group actions, meaning when you apply G to a point X in X and then apply P, it's the same as applying the related group element in H to PX. And then here is a co-cycle condition on A, means it's compatible with the multiplication in the transformation groupoid GX. G left time L times X. Actually, this orbimorphism later gives a homeomorphism between the associated transformation groupoid. Before introduce it, first I will say we call the map A cocycle and write P comma A to denote the orbimorphism between these two partial dynamical systems.
I have a question.
Yeah.
Can this notion of equivalence, orbital equivalence, can be rewritten purely in terms of associated groupoids?
Purely
Because
iterate.
on the previous page, you introduced the notion of a groupoid associated with a partial X.
Yeah.
And now we are talking about orbit morphism in terms of these partial actions.
Yeah.
So my question is, can be this orbit morphism between actions written in terms of groupoids?
Yeah, of course. Here is a lemma. So when we have an orbimorphism between the partial dynamical system, then we can define a continuous homomorphism from this transformation groupoid to the other one, given like here.
Okay.
Yeah.
So why it is not a definition, but lemma? It's much clearer what is going on without the several points to check.
Yeah. It's actually this definition is for this homomorphism. Yeah. And then actually
okay. Mm-hmm. Yeah.
And then actually now we can form a category. So first let me introduce this lemma definition. So when we have two orbimorphism, say one from G acting on X to the group H acting on Y, and another from H acting on Y to K acting on Z, we can combine them into a new orbimorphism. The idea is that we apply second morphism to psi after the first one, and this creates a new map that goes from G acting on X to K acting on Z. And then to create this combined morphism, we also define a new cocycle C, which tells us how to translate between G and K using the two cocycle A and B, especially for any element G and a point X. We first applied the cocycle A and then apply the cocycle B to get the collect action in K.
I have a very similar question as before.
Yeah.
Can this definition or lemma definition can be rewritten in terms of a bi-category of groupoids to compactify all these conditions and
yeah, after that I will explain it soon.
Aha, okay.
Yeah. And then here we can define a composition of these two urbane morphism. And then the composition between urbane morphism is associated, also has an identity. So what I'd like to say is that we can form a category denoted by PDS, where the objects are partial dynamical system and the morphism between them are urbane morphism. And then actually this is a theorem. There is a fully faithful functor from the category of partial dynamical system with urbane morphism to the here is a topological groupoid with continuous homomorphism given by this partial dynamical system to the associated transformation groupoid and the urbane morphism. This urbane morphism goes to this map between these two transformation groupoid. So here is a, let me recall the definition of the fully faithful functor. So a functor is called faithful if it is injective on Hom set and full if it is surjective on Hom set. So a functor that is both injective and surjective on Hom set is called fully faithful. So again, here is a theorem. So here is our one of main theorem. So given two partial dynamical systems, so the following are equivalent. The first one is these two partial dynamical systems are isomorphic in the category of partial dynamical system with urbane morphism, and is equivalent to the associated transformation groupoid are isomorphic as topological groupoid. And there are a few more things, but to explain this, let me introduce some notions. I will explain it later again. So this is studied by Lin. So two partial dynamical systems are said to be continuous orbit equivalent if there is a homeomorphism between the space X and Y denoted by P. And in addition, there are two continuous maps A and B defined like here. And these maps satisfy the following condition. When applying the group action on X, and then applying the homomorphism P, the result should match the action on Y transformed by the map A. And the same thing is hold for the inverse of P. And then this triple PAB is called a continuous orbit equivalence.
But just a quick question. You have your which is defined on this. This is like a disjoint union, yes, of this.
Yeah.
So you have for every element in your group, you have some open set. So the map from this disjoint union being continuous means that you have a collection of maps and each of them should be continuous, yes? So in other words, instead of calling it 1A, you can also think it like a collection of maps,
Yeah.
A subscript G, indexed with these elements of this group G, and each of these maps should be continuous, yes?
Yeah.
This domain is a disjoint union as a topological space, yes?
Yeah. Disjoint
Okay.
union.
Okay, thank you.
And then given a partial dynamical system, the stabilizer consists of all group elements, then leaves X unchanged under the action. Then this set turns out to be a subgroup G. And then the essential stabilizer is a bit more subtle. Here, instead of just looking at what happened to X, we look at all points in some neighborhood around X. We collect all group elements that fix every point in some neighborhood of X. So even though this is stricter condition, this set still turns out to be a subgroup of G. So we defined here is a stabilizer subgroup, and here is the essential stabilizer subgroup of G.
So I'm a little bit confused. This is essential stabilizer is much smaller than the general stabilizer, yes? This is like intersection of this. And I'm confused since usually in mathematics, when something is called essential, it usually means weakening some condition. For example, in this K-homology business, there is the notion of being, for an operator being essentially normal, and it means that it is normal up to compact operator. So this is something weaker. Here you have something stronger, yes?
Yeah.
Okay.
On the other hand, you have stuff like essential spectrum, which is again like a stronger condition. The essential spectrum of an unbounded operator is usually smaller than the real,
Yes, it's
like
smaller.
the actual on the no spectrum.
Yeah, but it is smaller since there is easier to be invertible in.
Yeah, sure, you could do that,
Yes.
but then you just apply a negation in the right place, and now it's an easier condition.
Yeah. Okay.
So essentially, you can use it both for weakening and strengthening.
Yeah, that's a good sum.
In fact, we always are.
Sorry, can you explain this in the case of the global action? Because if you have a global action, for instance, of a compact Lie group on a manifold, then you have the composition of your manifold into orbital classes, okay? Orbital types. Is this idea somehow parallel to this in the case of partial actions?
Pardon?
So in this the composition into orbital types, you are take together all orbits having the same stabilizer. So now you have some local condition, which maybe is the only one which is appropriate for partial actions. But my feeling is that these ideas are parallel.
Yes, it's a generalized notion for stabilizer group for the global action.
So can I think about this as a kind of local or maybe partial orbital type?
Partial
from
orbit?
global axis. Can I?
I don't know.
Mhm. Okay, thank you.
So sorry.
Okay, go ahead. Go ahead.
Yeah. And then when we have this to map PA, we say PA preserve stabilizer. If the stabilizer group at its point in X is matched perfectly via A to the stabilizer group at the corresponding point in Y. Then similarly, PA preserving essential stabilizer if the same kind of matching happens. But now, instead of just looking at what fix a single point, we look at group elements that fix a whole neighborhood around the point. Now, here is a theorem again. So, the two partial dynamical systems are isomorphic in the category of partial dynamical system is equivalent to the corresponding groupoid are isomorphic, which is also equivalent to the fact that there is a continuous orbit equivalence between these two partial dynamical systems, such that A is cocycle and PA preserves stabilizer. Also, it is equivalent to the fact that there exists a continuous orbit equivalence between these two partial dynamical systems, such that A is cocycle and PA preserve essential stabilizer. And moreover, if the essential stabilizer group are torsion-free and abelian for X and or Y, if these two essential stabilizer group are torsion-free and abelian, then it's one of the item. This things is also equivalent to this one, meaning there is an isomorphism from this cross product having a diagonal preserving one. Next, let's move to partial action of the free group. So here we start with the free group denoted by F, generated by a set A. For any element G in the free group, we write here to mean the ranks of its reduced form. And so here, suppose the free group F acts partially on a space X. Then we define two important properties of such a partial action. The action is called semi-saturate if whenever two elements G and H of the group multiply without cancellation, meaning the length of GH is exactly the sum of the length of G and the length of H, then the action of GH is just the composition of the action of G and H. Then a semi-saturated action is called orthogonal if the domain of action for different generators are disjoint. That is, if you pick any two distinct generators, their domains do not overlap.
I have a question about this orthogonality.
Yeah.
Is this condition being orthogonal defined in the context of the partial action of a free group only, or is it general for all partial dynamical systems?
No, Thomas, I think that you need generators. Those alpha and beta belong to the set A, and this is the set of generators.
Yeah, but free generators?
Probably.
Do you need freeness of the generators?
So probably you have some set of generators, and this is like length 1 words in this free group. Yes.
It's the top line of the slide. Is that this is the free group on A?
So only for generators alpha and beta. Okay, thank you.
Yep. And then in this case, we can define a diagonal system. To do that, we first collect all domains where the generator acts, and then we call the set U, and it's simply the disjoint union of all the individual domains for each generator. And next, we define a map, which we call sigma, from this set U back into our space X. For each point in U, if the point belongs to the domain of a generator alpha, then we can apply alpha's inverse action to it. And then we have a diagonal system X sigma. And then when we have a orthogonal semi-saturated partial dynamical system and the corresponding diagonal system, then there is an isomorphism of topological groupoid from this transformation groupoid associated to this partial dynamical system to this diagonal groupoid associated this diagonal system, given by like this. So we have, the point is we have a topological groupoid isomorphism.
Sorry, I don't understand this. So this time, alpha and beta, they are what? Generators of F?
Here?
Because I see here the length. If these are generators, just for the length is 1.
Finite word is reduced, maybe.
So this time alpha and beta mean finite words.
It's positive cone. It has to be in positive cone.
Not trivial finite words.
Somehow like words that you would find in C intersets. The way I see it.
So reduced simply means that if you have X and X inverse or X inverse X.
Yeah, the GC matrix.
In a free group, these are the only relations.
Yeah, the GC matrix is 0.
Okay.
0 entry.
And then for an orthogonal semi-saturated partial dynamical system, we always have torsion-free abelian isotropy subgroupoid of the transformation groupoid. So here is the...
Are we going to explain this result?
Yeah.
So probably that being torsion-free somehow easily comes from freeness. But why it is abelian?
Abelian also comes from... I forgot.
Essentially, this group is going to be isomorphic to a subgroup of the integers. So that's why it's going to be a torsion-free abelian. Because there's an isomorph between this groupoid and the Renault-Diaconal groupoid, and there all isotropies are going to be subgroups of the integers. So they're torsion-free and abelian.
So it's a product of copies of Z.
Yeah, each of the isotropic groups is going to be some kind of a subgroup of Z.
So the number of copies, I suppose, is equal to the number of generators.
No, it has to do with how the action works, but not exactly the number of generators.
I don't understand this.
So probably, maybe it is right to think that if you act with something which is free, it is very difficult to fix something, but I don't know whether it is a good intuition.
As I remember, to show that this isotropic groupoid is torsion-free and abelian, to show that actually we focus on the essential stabilizer group is torsion-free and abelian. Because isotropic groupoid is a union of stabilizer group times X. Because here is the element.
Because the isotropy bundle is just the union of the isotropy groups, and then we show that in this instance, each isotropy group is isomorphic to a subgroup of the integers.
Yeah.
They are not all the same, but they are all isomorphic to the same subgroup of the integers. Well, basically they're the integer or zero.
Yeah.
Yeah, there's something that we shown there.
Yeah.
Okay.
And then before I introduce another main result, we need to visit this definition. So here is sorry. So here, oh sorry. So let's consider a diagonal system. So we can also define two types of stabilizer at the point X. First, the stabilizer group at X consists of all integers that you can write as a difference Mn, where M and N are natural numbers, such that the both send X to the same point via sigma. The second, the essential stabilizer group is also considered difference M minus N, but now we ask for sigma to the M and the sigma to the N to agree not just at X, but on some open neighborhood around X. So here also essential stabilizer of X is contained in the stabilizer of X for each X.
Sorry, I have a question.
Yeah.
Why this is a definition, but not a proposition? That this is the description of stabilizer and essential stabilizer for the Diacono-Renault groupoid.
You mean why is
because stabilizer and essential stabilizer was defined before.
But
now we have definition which looks like a characterization of the stabilizers and essential stabilizers for the Diacono-Renault groupoid. or a system. Yeah. So why is that definition, but not proposition?
Yeah, one is not defined for groupoids, they are defined for the actions. So it's slightly different. So one is defined for maybe global action or partial actions, and this one is defined for the systems. It's not exactly the definition between the groupoids exactly. Of course, it's related to isotropic groups, but it's somewhat different. And also we took the definition from their paper there.
Mm-hmm.
Yes, in the paper they define this notion, and for us, we define this in the context of partial dynamical system.
Yes.
And then we can also talk about what's called the minimal stabilizer at the point X in our Decono-Luna system. And then this is defined as the smallest positive integer n, such that n belongs to the stabilizer group of X. In other words, it's the smallest number of steps where sigma repeats itself at X. And then similarly, the minimal essential stabilizer at X is the smallest passive n, such that it belongs to the essential stabilizer group.
Mm-hmm.
And then it's also defined by Carson-Ritz.
Sorry, I have to ask the following question. So you are writing minimum, but your stabilizer consisted of integers. Okay.
Yep.
So now you are defining the positive part of these integers.
Yep.
And then you are taking the minimum. Okay.
Yep.
So somewhere you are fixing the orientation of these integers. You are choosing some generator, and this minimum is something like what?
This says that when sigma when some point goes to be a sigma, and then how
Sorry,
this number,
may I?
Yeah.
You have your sigma, right? So sigma, so this defines one positive part of integers.
Yeah, exactly.
You had sigma minus one, you would have negative ones, right?
Yeah, exactly.
You have sigma. You look at powers of sigma, positive and negative.
Yeah,
sigma gives you orientation.
Yeah, thank you, Richard. Yes.
Sure.
Yes.
Okay.
I'm really sorry. And then let's consider the Decono system on one Uno space X with a map sigma, and another Uno space Y with a map tau. And then we say that these two systems are continuous or equivalent if there is a homomorphism P from X to Y, and there are some continuous functions that help relate the action of sigma and tau. The means for every point where sigma is defined, the image under P of its orbit under sigma can be matched with an orbit under tau, possibly after shifting by some number of steps. And the same holds in the other direction from Y back to X. So So we say that a continuous orbit equivalence preserve stabilizer if the following condition holds. First, a point x in X has finite minimal stabilizer if and only if its image P x in Y also has a finite minimal stabilizer. So periodic point corresponding to the periodic point under P. So simply the orbit equivalence not only match the structure of orbit, but also respect their periodic behavior, including the number of steps needed to return to the starting point. Also, we have a notion of the preserving essential stabilizer. So here is the last result. Given two orthogonal semi-saturated partial dynamical systems and their associated diagonal system, here are several statements that are all equivalent. They describe the same underlying relationship from different perspectives. The first, two partial dynamical systems are isomorphic in the category of a partial dynamical system. And then second, the groupoid built from this system are isomorphic as topological groupoid. And third one, and then there is a continuous orbit equivalence between these two partial dynamical systems, such that A is co-cycle and preserving essential stabilizer. And the fourth, there is a diagonal preserving isomorphism between the cross product of sister algebra and also the diagonal lunar system associate this partial dynamical system are continuously orbit equivalent. This is also equivalent to the diagonal lunar groupoid are isomorphic as topological groupoid. Also, finally, the sister algebra of groupoid are isomorphic with the underlying space matched. And so,
sorry, could you compare this theorem with the previous theorem in which you had 1, 2, 3, probably 4? So which points are new? 5, 6, 7?
Yeah, actually 1, 2, 3, 4 is the from the previous one. It is just for special case with a
so new points are which ones?
Now the new is 5, 6, 7.
6, 7. Okay. Thank you.
And then my talk is finished.
But you still have half an hour, so. You still have half an hour, so.
Oh, really?
You still have half an hour. I wrote to you, but it's a 90-minute talk, so.
Okay, can I ask a question then?
Yeah.
Might help. So if you replace, so FF prime are three groups, right?
Yeah.
Yeah. So what if you replace them like one of those rigid lattices, so high rank lattices? So instead of three groups, higher rank lattices. First of all, F and W prime are related how? So they have the same number of generators or something, or what? So you have these two groups, F and F prime, in your final result. In your final result, final theorem.
Yeah, final. I'm sorry. I
just
it's
here.
difficult to. Yeah.
Okay, so let's look at this one. So here F and F prime are free groups.
Yeah.
They have the same number of generators, I guess, right?
Yeah.
It
Same
follows
number
from.
of
So they're
generator.
isomorphic. Yeah, so they're isomorphic as free groups.
No. They don't need to have the same number of generators. It can be different. F and F prime does not have to be the same number of generators.
Well, they have it if you have the isomorphism between these two cross products.
Yeah, but the isomorphism between cross product does not imply that
No, but then
isomorphic
K1
group.
number of generators in this cross product number of generators given by K1, right? Those cross product.
No. Because one of the examples that we have is for graph system algebras, and there the number of generators is the number of edges. And we don't need to have the same number of edges to have isomorphic graph system algebras.
That's surely true. Yes.
Oh, yeah, okay. So you mean that, yeah, because it's partial. Okay, it's partial system. Okay, so you don't really say very much about those. Okay, but then why do you care that they are free groups?
It's just there are a lot of examples, for instance, graph system algebra, where we use free groups to define a partial dynamical system that gives us the algebra that we want. So, as I said, one of the main examples of graph system algebras.
No, okay, sorry, I am slightly confused here, right? Because you are looking at your partial dynamical system, right? So basically you have a so what do you have? Pseudo group, right? You have bunch of open subsets of X, say f acting on X, open subsets of X, and you have partial homomorphisms between those and compositions, right? Of these partial homomorphisms. So that's your partial dynamical system. So saying that you have free group there is kind of a spurious statement, right? So free group is not free groups don't really appear in your constructions.
So you are asking why we focus on free group?
Yeah, why bother with free groups, right?
Because first to actually in our first step we want to study the continuous orbit equivalence for in the context of a Boolean dynamical system. I mean, and then actually the given a Boolean dynamical system, we can construct a partial cross product from it. And that time we use a free group.
No, but you're not really using this free group, are you? Because because you could work, say, your partial dynamical system, you have free group which acts trivial everywhere.
Yeah.
Right? But in your results, this free group does not show up at all. Right?
In this one in particular is how you can define this diagonal system from a partial dynamical system. Because if it's just a general one, it does not give but just one map. You have all the action of the group. But for examples where you have the partial action of the free group, actually it's kind of like a lot of the elements of the free group will just act as an empty function. And so what really matters is just this one system, which is this Dynamical system. That's why we have these results. So as I said, one of the main examples that we're interested in is graph system algebras. And then in graph system algebras, you have a lot of ways of building the graph system algebras. One of them is using partial action. Then you have a partial action of the free group generated by the edges. And then there's another way of looking at the graph system algebras, this diagonal system, where you look at this boundary path space of the graph, and then you have this just shift map. And then what we are doing here, just generalizing this to any kind of system where I have this action of the free group, which is orthogonal and semi-saturated.
Okay, I'm sorry, I still have the same problem. So if you think about the graph, so your free group is supposed to be given by generators of your free group are supposed to be given by edges, right?
Yes.
Right, but when you just give yourself a set of generators of a group, whereas the fact that it's a free group, well, it's not a free group actually, right?
No, it is the free group
You can
generated.
always map a free group. If you've got the generators, you can always, of any group, you can always take a free group and map it onto it, right?
Yes.
But somehow with this free group part does not appear. You
No,
have
it's the group that
relations,
acts.
right?
No, but it's the group that acts in some space. You need an action of a group somewhere, a partial action. So the group
Yes,
that acts is the group.
yes, but there can be quite different groups with the same with actions the same, right? As said,
Oh,
you have say you have trivial action, right? On space.
Yeah.
Any free group acts trivially on the same space, right? And as dynamical systems, you get the same dynamic as this partial dynamical system. You get the same partial dynamical system in your definition, right?
Oh,
Well,
because
if you want the isomorphism, then what's the word? If you have this done before, right? Then somehow F does not appear. If your group acts trivially, it's if you just have loops, right? Nothing else.
but then the cross product is just going to be.
Well, then the cross product is when you don't get a cross product, then you kind of you throw out the stabilizers, right?
Yeah.
You may have, in the case where, say, you've got two free groups of different with different numbers of generators, some of the generators may have empty domains though, and then this won't turn up in the thing. And then by asking with the orthogonality condition at the start that the things each have distinct domains, you may be able to get around this. So you could have artificial symbols in the group that don't just do the trivial action, they do worse. They don't act anywhere, they have empty domain.
Yeah, precisely. But so that's different. But that's kind of spurious generators that you add.
Sure, but you would still get the same partial dynamical system.
Yes, but it's no, but there's more than that because so suppose you have a loop in your graph, right? So you have each of the edges generates an element of a free group. J is a generator of a free group, right?
Yeah.
By definition.
Yeah.
Right. So, but it's not the free group that acts, but it's the cyclic corresponding quotient, cyclic group that acts. And in your cross product, it's a cyclic group that shows up and not free group. That's why that's why I have a problem. That's why I don't quite understand the statement. So partial dynamical system is example of partial dynamical system, right?
Yes.
Just dynamical system.
Yes.
Okay, so you have free group acting on X. Trivially.
Not necessarily. It may fail orthogonality.
What was orthogonality? The domains of each generator is different.
That disjoint. Yeah. So you can't trivially act everywhere, but
yeah, sure. But so imagine that your free group acts. All you have is a cycle, right? So your free group acts as a cyclic group of finite order. Yeah, obviously satisfied. So I talk about so it's not free group, but it's finite cyclic group.
No, it's still the free group because you have a cycle. You have all paths which are just translation of this cycle repeatedly infinite many times. And then an edge is going to act on this cycle only if you can add the edge at the beginning or you can remove it. So they act differently in each of the paths.
Well, No, I have a problem because you have composites say Z2, right? You just have two vertices and two edges. one and the inverse one, right?
Yeah.
So you have two generators and composition is identity, right?
Mm-hmm.
So you have a saturated.
No. The composition is not the identity. Because
Sorry?
if you have a generator, so if you compose, you're just gonna add, instead of adding one edge at the beginning, you're gonna add two edges. It's not gonna remove the edge.
No, I'm not removing anything. I'm just saying that composition one way and composition the other are projections onto your vertices, right?
That's when you go to the sister argument, but not when you look at the partial actions.
Partial action is you take one vertex map to the other and the other way.
No.
So what is partial action?
Because the action is not on the vertices. The action is on the backspace of the graph.
So the space consists of 2 points, okay?
You mean the space on which you act, right?
On which you act consists of 2 points.
Okay, but that's not
And
the
there is one generator which maps 1 point to the other, and there's the other generator which goes the other way.
Okay.
Right? Which is action of Z mod 2Z, right? So it's which is action of cyclic group of order 2. On the other hand, according to your definition, it's supposed to be a partial action of a free group on two generators.
Yes.
But then once you start doing cross product, you're just throwing away most of this free group part, right?
Yes.
Your cross product only involves Z mod 2Z.
Yeah.
So that's why I have kind of problem with what's the word? It's cross product by Z, partial action of Z. Because somehow you do not really, because you don't say third power. You've got free group on two generators, but the partial action is just collapses it to Z mod to Z action.
Yeah, that's fine. Yeah, that can happen.
So I would be.
That was what Jonathan was saying. That sometimes a lot of the elements of the free group is going to act as the empty function, so they are not going to appear in the cross products. That can happen. Yeah.
So you don't see so you don't really see this free groups in cross product, right? It's just kind of numbering of edges, right? No, not even that, because actually not even that, because you have your formula for composition actually basically says that you divide out by commutators, right? So the composition only depends on the length of elements, not on the elements.
But I don't see how you can remove the free group on the graph case in general. Have a quotient.
Somehow I can't see the. No, it's not a question of removing free group. It's just that this free group is not really. It's confusing simply when you're saying free group, because you have basically action of free abelian semigroup. So your condition there, your partial actions, your action, the semi-saturated, really says that you have positive semigroup. Says you have n to some power k acting. Because of this condition, right? Abelian, yes, abelian.
I don't think it can just be abelian though, because you could have one generator send an element from its domain into the domain of another element, and then you don't have commuting because even the domains don't match up.
No, but if they happen to match up, so if there is something in common domains, then they become both domain and codomain, right? There's of course it's a partial map, right? But if there's something common domain codomain, then they commute.
Yes, but only one generator is allowed to act then, because you have this orthogonality condition that says that the domains of each generator are disjoint.
Ah,
So
maybe
you have a copy of
yes.
Z working, that's true, but it's the copy of Z corresponding to one of the generators. The other generators are simply acting on other parts of the system.
So, Jonathan, are you saying that this freeness is reflected in this disjointness condition for the domains?
I don't know if
No, it's not freeness. No, it's just we are disjoint, right? We are defined in disjoints.
you could
with
you can make the
disjoint
argument to
domains,
say
right?
that it's a disjoint and maybe that's a better intuition for looking at this, but I don't.
Maybe, right?
I
Because
think that free in the sense that it is, yes, the free group surjects onto every other group with
onto
sufficiently,
everything,
yeah.
right? So it just
Yeah,
does,
but
yeah. So somehow,
but I think you need the freeness in certain circumstances. For instance, if you had the case where both the groups are, if you remove freeness and you consider one action by Z and the other by the trivial group, or Z mod 2, say, and you consider both the trivial actions both times with full domain, then the cross product C-star algebras will not be isomorphic.
no, wait a minute. So I'm not, no, of course not if you take full action, right? If you take full action, then so
well, but it's still a partial action where you only have one generator.
Yeah, if you have partial action with one. Okay, by the way, my problem is kind of spurious, right? It's nothing to do with your result. It's purely my trying to understand what's happening. That's all,
of course.
right?
Of course.
By the way.
We have time to do it.
Yeah. No, okay, reason I asked because on this other hand you have a situation where you have, say, some higher lattices acting on the minimal actions of the Polskel space, and you get similar result, right? So cross products are isomorphic, actually have stronger results, right? Cross products are isomorphic if both spaces are homomorphic, and the groups are isomorphic, and the actions are conjugate.
Yeah.
And somehow you might be, it seems somehow to be related to what you're saying here. Otherwise, I think you could get something stronger using actions of using this orthogonal, forgetting this orthogonal part and requiring that really it's really free group, so there is always place where any commutator is non-zero, is non-trivial. Then you might have stronger results somehow, because this orthogonal conditions makes it very rigid, right? You have your generators, they act different places, and the compositions depend on the length of the edges of a length of in the graph, right? For graph algebra, it's not so much graph algebra, but somehow your space consists of vertices and your edges are generators, and so on. And when this condition is actually that's kind of curious. No, and when your condition is no, your condition is not natural because GH might end up different place. No, because okay, if you have minimal action, then yes. So, but you need so you need some minimal action there. No, I was just thinking. So if you have a cycle in your graph, right? So you can go from one vertex to another 2 different ways.
Yeah.
Then there's kind of problem with this condition number one, right? But the result of composition essentially depends on the distance from one point to the other. But if you've got different distances, then the results might be different, right?
No, but that's the thing. The action of the free group is not on the vertices.
It's not, sorry.
It's not on vertices.
These very
No, yes, vertices is your X. Space X is the set of vertices.
No, but for in order to get the graph system algebra, X is just the set of paths, not of vertices.
X is set of what?
Paths.
No, but I'm taking an example, okay, of the action. Take a graph. Now call your X, space X, would be set of vertices. And generators of F will be edges. Because over
Yeah, but in this case, if you have two edges arriving at the same vertex, it's not going to be orthogonal. So if you have,
yeah, so you're making it. Yeah, that's right. So. Yeah. Okay. Okay. Accepted. No, it's kind of a bit. It becomes fairly rigid. This orthogonal, semi-saturated orthogonal.
Yeah, as I said, for paths, it's just saying that if you have two, let's say you have an edge E, so this edge E can only act, or actually the inverse of E can only act on paths that start with E, when you remove the first edge of the path. So if you have two paths starting with different edges, they're gonna have be in different domains, so they're gonna be orthogonal. Because you just take a similar set of edges, there are mutually disjointed edges are different. So
yeah, it's space of paths. Yeah. Okay.
Yeah. So for the generators U alpha, in the case of path, is just the path starting with alpha. Alpha is an edge. Path cannot start with two different edges.
So. So basically what you are doing is saying, so let's take a, say, Cantor set, right? Total disconnected set, and a covering by a disjoint union of Klopen sets. And for each one of those pickups have some local homomorphism to something.
Yeah.
So when is that going to be? Well,
so if you choose just one local homomorphism for each of these disjoint union, parts of the joint union, then you can generate a partial action with the free group, same saturated. As once you know how the generators work, then there's only one way of extending it for any.
So for each one, so for each one, just pick up. So that's your structure, right? So for each one, you pick up a homomorphism. So basically, you said that you have your family of open sets, and you choose a bijection, right?
Yeah, choose a bijection.
Of this bijection of the set with itself. Bijection of the set of, right?
Yeah.
With itself. And the elements of your bijection, that's what you call generators of free group. Because somehow this condition one becomes almost automatic, right?
Yeah, because you define it, if you have just one homomorph way to generate it, then you define it in the way that works.
No, but you don't have really any choice, right? So you have your generators and open sets, and what's the word? And you know that union of these U alphas is your whole space, right?
Not necessarily. It could be. It's not always.
Well, if you have something not in the union of these U alphas, then you can throw it out, right? With nothing X on it.
Oh, the identity of the group acts on it.
Yeah, sure, but so you just don't bother with it. Then that's identity, right? So that's complement of the union of those is another open set. So it's covering, right? And the only thing you are saying is there's if these alphas are non-trivial, so there is this open subset maybe for which you have a trivial identity. So the way you formulate this is that alphas, these are generators, so without unit. If you throw in, if you throw in unit, then that's what you have, right? So essentially, you have union of U alphas plus complement. Complement nothing, right? So on this union of P alphas, you have bijection. From A to A, right? From set of symbols to set of symbols. And that's your structure, right? As far as I can see, I don't know. Or maybe, no, maybe not. No, maybe not. Sorry, no. It's more interesting than that. Sorry. No, you have a map from U alpha to union of some different U betas, right?
Yeah.
Not to single one, but to union of others.
Yeah.
And then you have a combustion of generates. Okay, yeah, no, sorry. It's still kind of action of and of commutative semigroup for my taste, but it's certainly easier to formulate it this way, the way you wrote it.
But it does not need to be commutative, because if you take an edge in a graph and then you add one edge and then another, it's different from you commuting them.
No, you can't say commutative or not because you have a problem of domains, right?
Yeah, you have a problem of domain.
But problem is domain. Problem is not commutativity.
But even if
Somehow.
the domain, you have an intersection of the domains, it's still not commutative. So for instance, let's say you have the O2 graph, just one vertex with two edges. Then the space that's where is just infinite sequence of, say, 0 and 1s.
Okay.
So if you actually 0, you're just adding 0 at the beginning. And if you add 1, you just add 1 at the beginning.
Mm-hmm.
So if I add 1 and 0, and 0, 1 is going to be different. It's not commuting, even if the domains are all the same.
I don't know if everybody has the same problem, but Gilles, when you speak, there is such absolutely horrible echo, but I don't understand a single word of what you are saying.
Yeah, there is a problem, yeah.
Maybe it's some microphone that's open.
Could be. No, but okay. I understand. At least I understand what you're saying.
Okay.
It's a feedback.
Okay, there's some feedback loop somewhere, and
yeah. Well, I can hear feedback somewhere, so.
Yeah.
Can you hear me normally? Actually, apropos.
Yeah. When you speak, Richard, there is no feedback, and it's okay. When Onji speaks, also there is no feedback. But when Gilles speaks, there's a horrible feedback, and also I can hear some feedback when I speak. So
I don't know.
Very bizarre.
Okay, but I don't have more questions. Thank you for the lecture, by the way.
Yeah, thank you, Richard, for saving the day. Much. Okay.
I didn't save the day. I was just asking questions.
But yeah, but this is what saved the day. All right. So, are there any other questions?
I have a question.
Do you know some similar results about equivalence of actions of inverse semigroups?
Inverse semigroup?
Yes.
Similarly, I've never seen about the inverse semigroup.
Now there is
some
a
funny
worse noise. I don't know whether you
noise.
also can hear it.
Yeah, I could hear it.
I lost your answer.
She said that she never saw inverse semigroup.
Ah, Jesus. Okay, thank you.
Anybody else? Adam, Jonathan?
No, thank you. I'm happy.
Okay.
I'm also happy.
Okay, that's very good. I have a very simple question. What I was missing in your talk was an example. I would like to see some illustrating examples of what you were saying. I don't work every day with partial actions, and to see some nice natural example would be very good for me, especially that from what Gilles was saying, it seems like you have some nice examples in graphs. So this is what I was missing. Yeah, but I don't know if you can generate it offhand. You would need to be able to write on the screen. If you don't, let's forget it. So this is what I'd like to see. If you can maybe at least, without going into details, give me an idea what would be a very natural and simple example for your talk.
Actually, I have an example related with generalized Boolean dynamical system, which is a generalized notion of a graph.
Okay.
But it's but as anyway.
You can write on the iPad, right?
iPad?
You have iPad connected, right?
Yeah.
How do you know it's iPad, not Samsung?
I can show you some. Let me give a second. Actually, we have some example, but it's very difficult to. The language is very. Can you see this?
Yeah. It's fine. We see it. Yes.
Yeah. The idea is. Here is an example, but it's very difficult to explain now, but shortly. Here is a Boolean algebra.
I think you have to enlarge the page because it's impossible to read the material.
Yeah, that's true. We have a huge screen, so we see it. But Ali is right. Please enlarge it. Yes.
But if I do this,
Smaller. Page is bigger, but fonts are smaller.
Yes, anyway, from Boolean algebra, and we can form an action between these two Boolean algebra, and then we can form on something like dynamical system, and then from it we can associate some we can also share some boundary something like boundary path space. We can define a partial action
In the middle.
and so from the free group. So we can construct a partial dynamical system from this Boolean dynamical system. So this is our example.
Well, a storm space.
And so we can also, from this Boolean dynamical system, we can get a diagonal lunar group point. Actually, we have this equivalence condition in the context of Boolean dynamical system.
Okay, so Boolean stuff. Okay.
Yeah, but it's very difficult to explain in details because the language is very
Dramatic.
Yeah, very horrible.
Okay. We had a different idea of what simple means, but okay. Okay. I believe that there is a lot of mathematical content. Yeah, you can really apply it in many places, and that's what's most important. All right. So if there are no further questions, and I don't see any raised hands, let us thank our speaker for a very interesting talk. Thank you so much.
I'd like to say something. I apologize for the poor presentation due to my Lego presentation, and I'm very sorry. It was my fault.
No worries.
No worries.
That's it today. Let me stop.
I would like to ask you to send me a PDF file of the PowerPoint of your talk. May I ask you to send me via email?
Yeah.
Yes. Okay. Thank you. I will send you an email for remind.
Yeah. Okay.
Okay. Thank you for your talk.
Okay, let me stop recording.
Thank you very much.
Yeah, thank you so much.